Fine. Okay. So thank you all for being here with us for the seminar by Maria Tsouri. She's an associate professor in the Western Norway University of Applied Sciences, and broadly the topic that she's working on is economic geography. This presentation is, if I understand well, basically a collection of some published and working papers. Maria, you have about 1 hour. People, please feel free to interrupt. I guess Maria is okay with this. And otherwise, you can, of course, write questions in the chat. Thank you, Maria, for being with us. The floor is yours.
Thank you very much for the invitation. Dimitris made a really great presentation of me. Yes, I'm an associate professor at Mohn Center for Innovation and Regional Development at the Western Norway University of Applied Sciences in Bergen in Norway. And my work, current and probably future work, is somewhere in between the geography of innovation and sustainability transitions. So the great challenges, like the environmental ones ahead of us, are global and systemic. This is especially true for the challenges related to food, energy, mobility, and construction. The systems that need to be adapted due to these challenges are large and complex, and therefore how we can bring the overall changes that the world needs on time. Achieving these ambitious and urgent societal objectives requires collective measures as well as private and public players to be put in motion and diffuse the transition. Globally, there has been a plethora of actions, policies, and innovations aiming to transitions towards sustainability. But what are actually sustainability transitions?
Maria, can I interrupt you?
Yes.
Can you please change the screen to the full
one? The problem is that now it's hiding part of my screen by people. I have to close here. Yeah. I'm trying to find a way to close your seeing the camera here. But anyway, so sustainability transitions. What are sustainability transitions? Transitions are long-term, multidimensional, and fundamental transformation processes. That's the most common definition by Markert et al., 2012, and are long-term, multidimensional, and fundamental transformation processes through which established socio-technical systems shift to more sustainable modes of production and consumption. And in general, this means change. Here we see the a simple count of sustainability transitions papers with and without original dimensions. So we can see that it's a fast-growing community and strata of literature. But how the literature on sustainability transitions has dealt with the space until now. The literature that the last decade distinguished two major shortcomings in the treatment of space by sustainability transitions studies. The first is that these studies were mainly single or comparative case studies, failing to explain the importance of the spatial context and treating space as a background variable. The second is the problematic usage of scale in existing transition analysis, and usually the territorial advantages, conflicts, and tensions are overlooked to a great extent, assuming that the transition will happen the same way everywhere. So I found two main frameworks that deal with space in this literature. To conceptualize better the spatial scale of sustainability transitions, Vincent Rufer, 2017, introduced the Global Innovation System framework. They introduced the concepts of subsystems nested inside the global innovation system, and the structural couplings between these subsystems. This framework has two dimensions: the technological innovation mode and the production modes, and the production valuation, which compresses which has characteristics like market access, financial investments, and technology legitimization. In the direction of relatedness and diversification, Bosma et al. 2017 proposed a cross-fertilization between sustainability transitions and evolutionary economic geography, using the concept of regional diversification. And again, we have two dimensions, that is related or unrelated regional diversification, and sectoral maturity level, if it is a niche or a regime. And going now to my own work, the main question of my current and probably future work is: how is knowledge and innovation in technologies aiming to transitions towards sustainability generated and diffused? So I have three contributions in this presentation that they treat this question in by different perspectives. The two first, they have the perspective of the organization or firm, and the third one, it is in the regional level of analysis. So the first contribution, which I will present today, has a title: Does participation in knowledge networks facilitate market access in global innovation systems? And it's the case of offshore wind. It's a joint work with Jens Hansen and Håkon Edersen Norman. And it was published in Research Policy. But before I go to the specificities of the paper, I need to talk a bit about the global innovation system. What is it? Vincent Trufer, in their paper, they introduced three improvements in all systemic theory. When we talk about innovation system theory, is theory on regional innovation systems, national innovation systems, technological innovation systems, and any other type of system, basically. And the first is the conceptualization of key system elements that and the context in which positive externalities, such as functions, emerge from a spatially open multi-scalar perspective. In other words, the question is not whether the territorial embeddedness of innovation processes matters, but how it matters and whether it matters differently in different technologies and industries. The second one is the dynamic perspective, able to explain processes that lead to the creation of new technologies and industries. And the third, they take into account for systematic differences between the various industries. So it consists, as I said before, as aforementioned, of two new structural elements: the subsystems of the GIS, where different resources form, and the structural couplings between these subsystems. In my way of looking at it, I see a series of nested subsystems where different resources form inside the global one. So subsystems are not spatially predefined. They are defined as network and institutional context in which resources form. But also it can be, sometimes they're described by boundaries. And structural couplings are showing how innovation depends on how actors combine knowledge, investment, markets, and legitimacy to new configurations. So these things need to, these configurations need to be linked, and these subsystems need to be linked. And these are the structural couplings, that they can cross regions and countries and generally borders, and also resources. There is a second contribution, theoretical contribution, by Rohe 2020 that differentiates between the formation of vertical and horizontal structural couplings. Horizontal are the couplings between regional resource formation processes, while vertical are the structural couplings between region processes of resource formation and factors or processes at the national or the global level. So let's go now to the paper, to our contribution. We started from the fact that renewable energy industries are largely international in terms of firms, knowledge networks, and markets. However, the access to these resources, to the international resources, is not given. Especially in industries characterized by technological complexity and not standardized markets, resources can be embedded in certain territories. It has been argued, and we would agree in this, that offshore wind is an example of such industry. So, therefore, based on the global innovation system and the structural couplings notion of Vincent Truffer and the differentiation in horizontal and vertical by Rohe, we made a quantitative attempt to trace a structural coupling between different resource subsystems, in our case, knowledge and market, and between different spatial levels, in our case, national and global. And of course, as a case, we focused on the Norwegian offshore wind firms and their access to the global market.
Well, Maria, can I ask one thing, please, in this slide? So, can you give us a bit more info regarding structural couplings? Your mic is off, I think. Yeah, now it's okay.
And for some strange reason, I cannot move the slides. Okay, now I can. So what I wanted, okay, these are the structural couplings in between. These structural couplings, they can connect. They are like channels. I see them as channels that they connect either resources, like let's say knowledge, regional knowledge, to the market, to regional market or national market or global market between them, or different geographical or levels between them.
Do they think about them as supply chains, or this is not relevant, it's something else?
It's a connection, it's established relationships.
Okay, I see.
You can see them as ties of a network, of a greater inclusive network.
Thank you.
Maria, so that's the way knowledge flows within this network.
Knowledge or market or in general resources, because now we are testing the knowledge and the effect of the knowledge. But in theory, there is no other paper on this yet, on testing other resources, how they connect and they are transferred from in multiple spatial levels, at least not quantitatively.
Before you continue, I'm stating my case of picking your brains, because they're planning to build such wind turbines, such a sea park in between Rhodes and Crete. And this has been given the go-ahead. So it is quite likely that at some point in the future, they will ask us our opinion. And, you know, as you go along, would it be possible to stress how lessons regarding diffusions, lessons that you identified regarding the diffusion of this technology in Norway may be important for us in Crete? Thank you.
Yes, actually, one of the conclusions is what are policy, the policy implication, we have important policy implications of this paper on how to make the consortiums of firms active in Norway in this case, because they don't have domestic market as well, and it's for places that actually they don't have domestic market. but they have industry on offshore wind. Because one turbine in Stavanger actually doesn't consider to be domestic market. So going on. Yeah. So we conceptualized, we draw on global innovation systems framework. And as mentioned, the global innovation systems consist of subsystems around certain functions, such as markets, or in specific countries, such as Norway. These subsystems can be linked between them. Whether and how such links exist is important. We therefore want to test how such links, the so-called structural couplings, facilitate access to resources in other subsystems. We know that firms engage in demonstration and R&D projects and participate in both national and international knowledge networks. We can therefore distinguish between the vertical coupling here, between a national innovation system like Norway and the global level, and horizontal coupling between knowledge systems and market systems. And we are going to test how these vertical couplings affect the creation of the horizontal couplings. To do so, we test for hypotheses that affect the different sources of knowledge and like PDP, like pilot and demonstration projects participation, the R&D projects collaboration, international and domestic collaborations, and collaborators from countries with domestic market of the Norwegian offshore wind firms on their entry to the international market. That are these collaborations and participation to knowledge networks affects their ability to join the international market, the international commercial projects. So we collected a sample of 178 offshore wind firms based in Norway, and that they are present in at least of one of the three data sets that we had. The first one is the 4C data set, that it has all the commercial projects, small scale and large scale, that are on in the globe, globally, that exist globally. And okay, I have to note here that we consider as global system, as global market, the European market. Offshore wind is an industry that is mainly European. Exist such firms in China, such farms in China, but they are close to shore farms, or offshore wind farms, that they use that they don't use the same technology as the real offshore wind farms, so they are excluded. The second database we used is the Cortis dataset. That it's the funded project R&D projects by European Union, and the R&D projects dataset by the Research Council of Norway. We recorded participation in projects and number of collaborators for all firms for every year from 2002 to 2017. So we created a ballot panel, and we also took into consideration the cumulative nature of knowledge. So we used cumulative time lapse of 3, 5, and 10 years. I'm not going to tire you with the econometry. No, first the variables, so we understand better how it structured this model. As dependent variable, we took the market participation that is represented by the large-scale offshore wind projects, and we consider it in both ways, binary, that is market presence or not, and count, like repeated market participation. As independent variable, we used international project pilot and demonstration projects participation in small-scale offshore wind projects. The R&D project participation, that is a number of projects funded by both EU and Research Council of Norway, in which a firm participates during the past period. The international collaboration, that is the number of non-Norwegian collaborators that a Norwegian firm has. The domestic collaboration, number of collaborators based in Norway that a Norwegian firm has, and collaborators in domestic markets, that is the number of collaborations of Norwegian firms that are based in a country with a domestic offshore wind market. And actually, not only it's a European thing, but until 2018 that we had this data, it was 5 or 6 countries, like and among them, if I'm not mistaken, is Germany, Belgium, Netherlands, UK, Denmark, and one by then wind farm in Sweden. So it's all of it concentrated in the Northern Europe. Also as control variables, we considered the age of the firm, the size of the firm, and previous or current by that time involvement in oil and gas industry. I'm not going to tire you with the econometric, as I said, which you can find in the paper, but I will go directly to the 5 results of our analysis. So first, we didn't find any relationship between the number of R&D projects that the firm participates and the firm's participation in the commercial project. The number of Norwegian partners in R&D projects had even a negative effect on firms' participation in commercial projects. And now the most important and positive results is that participation in demonstration projects has a significant positive effects on firms' participation in commercial projects. The number of international partners in EU-funded research has significant and positive effects on firms' participation in the commercial projects, and even more significant and positive effect has the R&D partners of the partnership with firms in R&D projects from countries with a home market.
Maria, wait a minute, go back. Go back one slide. So participation in demonstration projects had a significant and positive. What do you mean demonstration? Because in Greece,
pilot and demonstration projects are
not public demonstrations. Because public demonstrations against the wind farms, we've got a lot in Greece. And for a moment, I thought, okay, mea culpa.
No, PDPs, yes, pilot and demonstration projects. The small-scale wind farms. So this drive has driven us to the conclusion, the main conclusion of this paper, the theoretical conclusion, that is the vertical couplings in knowledge resources in national and transnational subsystems enable the establishment and the maintenance, in our case, of horizontal structural couplings between the different resources of the system. And this had also 2 main policy implications. First is that Norway has to stimulate domestic firms' participation in international pilot and demonstration projects. And the second one is the restructuring of the national R&D funding programs in order to include more international actor collaborations, especially with actors in countries with a domestic market.
So you know, if policymakers come to us, and I have a hunch that in earlier than a couple of years from now, they will drop us a line. What should we tell them?
If you want to make a domestic, to grow the industry of offshore wind, in this case, without a domestic market, because for now, Greece doesn't have a domestic market. But I think that I saw in that database also Greek firms. So in order to increase the participation of the Greek firms in the international markets, they should include more international collaborators especially where there is from places that they have already existing knowledge, that they have already domestic market. So there will be knowledge transfer in this case, and not only direct knowledge transfer, but also facilitation of the Greek firms to enter the market.
So, for example, Greek firm Mytilineos, they've invested quite a lot in producing wind turbines. Okay, I don't know if they produce them or they join the parts together, but they collaborated with at least 2 Danish firms that are working on wind parks right now. So that's what you're suggesting as well, isn't it?
Exactly. Increase the participation with international partners of home markets, of offshore wind farms' home markets. Yeah. I will pass the second contribution, that it has title Knowledge Recombination for Emerging Technological Innovations, and it's in the case of green shipping. So we pass from offshore wind to green propulsion. And it's also joint work with Jens Hansen, Thijs Hansen, and Marcus Ten. It was published in Technovation 1 year ago. And but before I start with the paper again, I will give some background on social network analysis, as it is my expertise and a different way of thinking. And it has its origins in epidemiology and computer science. Shifting, the difference is from the traditional econometrics is that it shifts the focus from the individual to the relationship between individuals. So social networks consist of actors that may be persons, firms, regions, countries, etc., and relationships that they may be formal or informal, friendship, collaboration, exports, and so on and so forth. Usually we don't sub in actors, we have to define the population, like all the offshore wind firms of a region, of a certain region, because if we do this, we lose information, we may lose information, but we can sample in relationships, and the relationships, as I said, can be formal or informal, that like contracts, collaboration, exports, transactions, or informal, that it could be friendship, meeting, kinship, or even drinking beer together. However, the latter, cannot be easily traced. So social networks, the biggest social network and most known one is the World Wide Web, which you see a picture of it here. It can be voters networks. It can be organizations producing a new technology networks, collaboration networks. It can be even your personal Facebook network. It could be recipes that interact in order, ingredients that interact in order to create recipes. It could be characters of Shakespearean tragedy. It could be members of Florentine families. Or most importantly, it could be how products are related between them. That, in this case, is a product space. So what we can measure with social network, that's important. We can measure things in actor level, that attributes of actors, gender, type, organization, and their centrality, their position in the network, how many connections they have, or if they connect different parts of the network between them, or how close to all the rest of the actors they are, and how many important connections they have. Then the second level is the dyad level, that is the relationship of tie, and then we can measure the existence or not of a tie, the direction of the tie, that is minus plus, or the strength of a tie. I sent to Dimitris 1, 2, 3, 5, 10 emails. That means the intensity of these relations. Then the triad level, that where we can measure structural force. For example, two actors have complementary resources of information. The principle of transitivity. In simple words, this means that a friend of my friend will eventually become my friend. So a person that I collaborate, that my friend collaborates, it's very probable that I collaborate with this person as well. And finally, the triadic closure, fully connected triad, where 3 entities collaborate with each other. Then in the network structure level, we can have random networks, scale-free networks like the internet, and most common in social structures is a small world network. Now going to our paper with my co-authors, the knowledge networks, we see knowledge networks as channels through which knowledge can be transferred across organizations, geographical borders, and technologies. The main mechanisms identified by literature governing the evolution of knowledge networks are the embeddedness of an actor in either social, strong ties, or structural contexts, weak ties of the network, the proximity of 2 actors, and the actor's status, popularity. While recent studies explore these mechanisms in a dynamic way, they are limited to the evolution of a knowledge network in a single technological field, sector, or industry. So we wanted to test if the same mechanisms apply across technological fields and affect the emergence of new technological fields, which in this case is the green marine propulsion, or in simple terms, green shipping industry. For our analysis, we employed...
Sorry for interrupting again. Just one small question here. So you said the word dynamic. I'm trying to understand if there is a time dimension here. So do we know anything about the over time appearance of the network? It gets stronger, it gets weaker, bigger, smaller, stuff like this?
Exactly. In dynamic social network analysis, here there is also automatic light. In dynamic social network analysis, we check the time dimension and the spatial dimension, evolution of the network. It's about the evolution of the network.
Thank you.
Then what you see here is like a screenshot. So what you do, if one network, one moment network, 1 year network, or one view of the network is a picture, like a photograph, then the dynamic way of it is the video. Okay,
Fine.
so
Clear. Thank you.
as exactly like in the video, we take screenshots. So because you cannot see the evolution in time, you have to break in year by year or in periods, in time windows.
Maria, okay. I'm not going to doubt your econometrics. Technovation is a journal that I have great respect. My question is more or less qualitative, and I would really love your opinion on this. If you look at the internet, I mean, it's a tool. I mean, it has connected us a lot. We are more, if you do an analysis, like a spatial analysis, the graphs you've got here, and we go past in time year by year up until 1990, we will start from a node and then it explodes with the internet. Yeah, so in theory, a lot of diffusion of information, but most of the time it's a lot of useless diffusion of information. And there's been a lot of work on this. I mean, Pierre Azoulay, a fellow that I really like, I mean, he keeps on publishing papers that basically explain that there are barriers, you know, information flows, but there are barriers to what we understand out of this information. So my question is, I mean, honestly, like it's a scientific query. It's not a question on your research. You know, do you really think that, you know, studies like this, and again, technovation is technovation, really allow us to see, you know, the end result, that the end result being we've got more knowledge? And this is like a very serious question for me, because we've got this global warming thing, which underlies all your research, and we really need to battle it, and people are doing a lot, but then you've got people like John Van Reenen and Nick Bloom saying that, you know, there's diffusion everywhere, but we never see any new results. We don't find any new ideas. New ideas are impossible to find. And I see diffusion everywhere apart from the results. That's what I'm trying to say. I see these nice graphs, and they look so nice. But in the end of the day, we keep on using ideas from the 50s, and all these new tools like the internet have not magnified our search space for new ideas. They have made us look with a magnifying glass on the same ideas we were using. So it's a philosophical query, I know, but what's your take on this? Now that I have found somebody who understands what I'm talking about, I need to pick your brains.
Okay, the diffusion happens. Okay, the generation of new knowledge, the diffusion of it happens through networks. Either it is internet or social networks or collaboration networks or knowledge networks. Then you have the adoption of the new technologies. That is a separate thing completely. Which one will be adapted? Which field will be promoted? And this has to do also with the institutions, the local or national or supranational institutions and their policies. So there are mission-oriented policies, for example, that pushes the generation, diffusion, and adoption of green technologies. However, there I doubt that they do it in a really organized way, considering the capabilities of each place in producing such technologies. But this is something in which I will argue in due time. And there is also the commercialization of knowledge. Like somebody has to buy the patent, somebody has to buy the result, somebody has to produce it to make the product. And that's a completely other stage. So I think that you are referring in the adoption and commercialization of this knowledge. However, the knowledge is there, and we saw in the recent years the booming of it through the internet and new technologies. And I mean, here it's full of electric cars that, in my personal opinion, is greenwashing. But in any case, you see electric ferries, something that I haven't seen until I come in Norway in my life, is to get on an electric ferry and go to an island. And I was surprised by it. And one of my main motivations on turning my research from ICT to green technologies. So yes, I believe that you are correct, but you are referring in another stage, and all these great minds and philosophers, and of course the problematization on this subject is on the adoption of these technologies, and that they follow other dynamics than the generation. And that's my personal opinion, okay? So, yeah. For our analysis, we employed dynamic social network analysis, as I said before, and more specifically, stochastic actor-oriented models. That is a permutation method that actually allows us to regress networks. Okay, so we had 1,136 projects that resulted to 3,719 actors. These projects include the green shipping project, biodiesel, biogas, bioethanol, electric battery and storage, fuel cell, hydrogen, and synthetic natural gas. However, only actors that participated in more than one project, they were considered 981 actors. And we excluded biogas, biodiesel, and bioethanol, as there were no common actors with the green shipping. So they didn't affect at all the evolution of the emergence of the new field. We had a period, we considered projects in a period of 2007 to 2018, and we divided in two periods, the FP7 framework and up to then Horizon 2020 framework. And we included the EU 27, UK, Norway, Iceland, and Switzerland. So in our dependent variable, it is the green shipping knowledge network from 2007 to 2018. And what we actually measure is the rate of change, like from non-existing ties to existing ties between the FP7 and Horizon 2020. And then as to explain this, we have social embeddedness for its green fuel during FP7. That's again, social embeddedness is defined as the rate of change from non-existing to existing ties during FP7. Then the structural embeddedness, the weak ties, as we were saying, for its green fuel for the FP7, that is and we defined it as a triadic closure of the network for every technological field during FP7. And the idea is that if one actor was collaborating with two actors during FP7, then these two actors will collaborate during Horizon 2020 in the new network. So then we considered institutional proximity and organizational proximity. Of course, they are slower in changing. They change, proximities change, but not as fast as the connections. So institutional proximity is defined when two actors are located in the same country and therefore in the same institutional context. And then organizational proximity when two actors are of the same organizational type. They're both firms or universities. And then we defined actor popularity or status for its green fuel during FP7 as eigenvector centrality. That means the importance of both the importance and number of connections of its actor were considered. Their connections to other central nodes and how many they have of them. So again, I'm not going to tire you with the econometrics. They are all on the papers. What is important is the findings. So in general, in previous collaboration in established technological fields, the previous collaboration in established technological fields affects the collaboration in the emerging field. Similarly, if an actor collaborates with two actors in an established field, these two actors are probable that they will collaborate in the emerging field. Organizational and institutional similarities between actors are important for their collaboration in the emerging field, while we used as control the geographical proximity, that it wasn't playing any role. And the status of what it was different from the existing literature on the evolution of the same technological field and not across fields as we do, is that the status or popularity of an actor in an established field is not significant for the collaborations of in the emerging fields. That means that an actor doesn't transfer its own popularity, its own status across fields. So it starts from scratch to build the network. So this also has some policy implications. The development of the networks of the established technological fields affects the emerging technological field network development. Therefore, we have to keep in mind that clean tech does not develop from scratch. It has also path dependence. This is relevant for mission-oriented smart specialization policies, as our approach can support the identification of areas in which matchmaking between established and emerging fields seems favorable. And this is the contribution of this paper, the main contribution. So, yeah, now I have a third contribution in which I will give a bit more details. This is a work on progress. It's a working paper with Ron Bosma from University of Utrecht, and it's about the importance of science for the development of new photovoltaic technologies in European region. But first, I want to explain what is relatedness. Okay, as aforementioned, technological knowledge and innovation do not emerge out of the blue. Knowledge is also not distributed equally across space. Regions differ in their capabilities to produce new knowledge and therefore follow different technological trajectories. The kind of technological knowledge developed in a region depends on the variety of knowledge in a region and the extent to which the pieces of the local knowledge base are related. So therefore, relatedness refers to the proximity between the different knowledge elements in terms of their utilization and their cognitive content. The notion of relatedness has been applied to explain how regions diversify into new activities. Relatedness constitutes an important driver for the diversification of regions into new technologies, according to the literature. As regions extend the scope of their activities around technological competencies they accumulate over time. Regions that are specialized in technology diversify more easily in a technology that requires a related knowledge set because it entails lower costs and risks, and they can build on existing regional capabilities. And now an example is that actually if you have region A that produces textiles and region B that produces, let's say, motorcycles, that's a very random example just to make you understand what is related to diversification. The region B is easier to diversify to airplanes with lower risks than the region that has skills and competencies on textiles. And that makes some sense. And that's why this concept is this concept of related diversification is a key pillar of smart specialization policies. Is the way that regions diversify to new technologies in general, an evolutionary approach of it. What happens though in green technologies? Study shows that the development of green technologies in regions is subject to a similar related diversification process besides the role of green policies. And green policies, as I was saying before, like mission-oriented policies, highlight the global challenges and dictate the development of green technologies in regions. Sometimes they don't, without taking into consideration the regional technological capability. So you have, for example, a policy saying, oh, you have to produce photovoltaics, you have to make your cars electric, but in the end, to produce more electric cars, for example, when you have an industry of electric cars. But if you don't have the competencies to do so, it will be risky for you as a region. Knowledge capabilities are different across regions, and they play an important role in diversification at the end. At the regional level, studies confirm that technological relatedness enhances green regional diversification. And interestingly, in certain cases, regions even relied on local capabilities in fossil fuels when diversifying into green capabilities. For example, for offshore wind, it's very relevant, the oil and gas industry.
Maria, sorry again for interrupting. Just a clarification regarding green diversification. So this has to do with me not using fossil fuels anymore and using something else, or using green sources, but many of them?
No, it's like for a region to go to a green trajectory, to start producing knowledge, or in other papers, because I'm dealing with knowledge, okay? But in other papers, it's production or skills, even in labor skills. It has a similar effect or industries to become, to have green, to enter a green industry, okay? To start being green. But in the same time, it needs to be consistent with the capabilities that a region already has. And sometimes these capabilities are not green.
I see. So it doesn't have to do with me using a variety of green technologies. Even if I use one, it's still diversification, correct?
Exactly. If you pass from a fossil one to a green one.
I see. Okay, fine. Thanks.
So, yeah, where I was, apart from technological knowledge, also scientific knowledge may also be important for green diversification. So scientists are involved in highly localized research activities, and they develop ideas mainly within their own scientific domain or close to that, in a related one. This makes regions accumulate pools. Pools of scientific competencies that evolve in a rather similar way with technological competencies and are reflected in the specific scientific profiles of regions. These scientific regional specializations may affect the ability of regions to develop new technologies. And this may also be important in the case of green technologies that rely primarily on codified knowledge, such as photovoltaic technologies. Regional scientific capabilities are expected to play an important role. However, there is little research about it in the green diversification, and especially in the scientific capabilities, connected to the scientific capabilities of regions. And to answer these questions, we developed two hypotheses. The first one, if regions are more likely to develop a new green specialization when they have a scientific specialization in the same domain. And the second one is if regions are more likely to develop a new green specialization that is related to their local scientific capability. In the same time, it's not important, and it's not only found the knowledge inside the region, right? It can be imported from other regions. And codified knowledge is it's much easier to be transferred in transnationally and transregionally. There is also there is an inflow of scientific knowledge that may enhance green diversification in regions, but there exists little research on this topic. A key insight is from the literature is that regions have a better capacity to develop new technologies when having access to external knowledge they do not possess themselves. And more recently, studies have shown that complementary interregional linkages are important for the development of new technologies in regions on top of regional capability. So what is not yet investigated is the extent to which scientific knowledge sourced from other regions makes a difference in this diversification process, and for green diversification in particular. So we developed two hypotheses testing this. The first one is if regions are more likely to develop new green specializations when they source scientific knowledge external to the region overall in absolute numbers. And the second is if regions are more likely to develop new green specializations where they source related scientific knowledge external to the region. So you would ask why photovoltaics, right? Photovoltaic is one of the most established renewable energy technologies that contribute to climate change mitigation. And although it's a technology that actually it was born overseas, Europe was central in its production, while today it struggles with the Chinese competition. Although in European actions like Green Deals highlight the use of renewable energy technologies, there is a lack of strong policy. There was until recently a lack of strong policy on photovoltaics. However, the latest policies support the development of PV technologies in the EU in order to reduce the EU emissions. So the different photovoltaic cells, technological solutions, different photovoltaic technological solutions, alongside with the complementary concentrators, conversion and connection to the grid, and of course the generic photovoltaic applications constitute the different photovoltaic technological segments that are summarized in the table. PV technology and its segments is a relevant case also in research terms for exploring green diversification, as technology has high degree of standardization, They are extensively, it is extensively based on R&D knowledge, and a big part is patenting and other codified knowledge, such as scientific publications or projects. It is the oldest, one of the oldest after the hydroelectric technologies that actually was developed. There are patents since 1950s. And because of its early development and high standardization, high degree of standardization, there are multiple photovoltaic technological segments with distinct technological and economic characteristics that need different knowledge elements to be developed. Some of them, they are competing, like the photovoltaic cells between them. They're competing technologies, and some of them, they're complementary, like photovoltaic cells with concentrator or the grid, because all of them, they need to be connected to the grid. PV technological segments may require different regional capabilities to emerge and develop, and this is very relevant for our research. Data collection. We use the PatStat database to identify all granted patents in photovoltaics for the period 1998 to 2015. We selected all granted patents with a cooperative patent code, the CPCs, on photovoltaics in 31 European countries, as we said, EU 27, UK, Iceland, Norway, Switzerland. We selected patents with at least one inventor located in one of the European countries. The CPCs of photovoltaics consist of 12 subclasses that represent different technological segments in photovoltaics. We geolocated all inventors in NUTS2 regions, that is the regional level, nomenclature of statistical regions, and assigned patents to these regions, geolocate according to the inventor address. We made sure that we have only granted patents, and because a patent can be published multiple times, we made sure by using the application number that is unique. So we identified in total 12,296 unique patents on photovoltaics with at least one European inventor. With the use of keywords, photovoltaics, like photovoltaics, PV, solar energy, we extracted from Scopus scientific publications on PV technologies. We focused only to scientific publications with at least one author located in one of the European countries, and we identified 23,426 scientific publications for the entire period. After we used specific keywords for each one of the categories in order to identify its PV technological segment and to correspond the PV scientific segments to the PV technological segment. Finally, we attributed, we geolocated, of course, again, the publications to NUTS2 regions, and we, according to the affiliation of the authors. And finally, we attributed its scientific publication to the scientific field it belongs through the journal that they were published. For doing this, we use the Scopus journal classification that actually divides attributes to its journal certain scientific fields. Similarly to the scientific domains that are considered related when they cite each other, technological segments can be considered related when they cite similar scientific literature. So for all granted PV patents with at least one inventor based in Europe, we extracted their scientific citations. The citations of patents to academic journals. These scientific papers can come from authors all around the world. We didn't restrict it. They represent the scientific knowledge external to the region on PV patents, with PV patent source. And there were in total 6,457 scientific papers cited by PV patents during this entire period. And finally, we geolocated them by the author's affiliation.
Maria, sorry to butt in. Okay, so Are these USPTO patents, EPO patents?
They're all patents.
Okay, so I'm assuming OECD patent.
No, it's not the OECD database is the RegPat. Well, that includes the EPO and the US one. While this one is the PatStat that includes also from other countries.
Okay.
Other patent offices.
I draft patents.
Mm-hmm.
My advice to you would be to find a control group. The way you describe it, and I could be wrong, there will be a lot of double counting. The same patent reappears under different numbers again and again and again and again. And if you read it, it may manifest itself in 20 different patents, but it will be identical claims, etc., everything identical. And it depends on certain strategies that firms play. Mm-hmm. Furthermore, the same patent will manifest again itself in different other countries. So, you patent in the USPTO and then in JPO, Australia and South Africa, the Netherlands, and with the so-called unitary patent in the European Union, things have gotten even more perplexed. So there may be a lot of double counting. Because the query on photovoltaics and PV and everything, when you run a query, you run it on the abstract, on the description, on the claims. I'm saying this, but because it could give you drastically different results. I mean, when I say drastically, 20% different.
Mm-hmm. I will check. I will make a robustness check of this. That's the standard process of all these type of publications on how they're treating patents.
I know
most of the
standard process, but it's wrong.
Yeah. I could diversify, but yeah. Thank you. I can notice it, by the way. What query do you?
Look, for example, here you play with circuits. So you need to have multiple queries that have additional words. I can suggest a patent attorney that works on this. Mm-hmm. And you need to work with them. So he will tell you how he would go about in searching for patents like this. And I have a hunch that if you do it properly, you may end up with something like 10% of your sample. That big of a difference. I know everybody's doing it this way. Okay, but
because we didn't make any content analysis. We just used the CPC code, and then we checked it with the application numbers. It's unique. Don't.
Application numbers, a lot of times, they will give what you think is a patent is an application.
Yes, but it has also selection, is granted or not.
Granted where? Again,
if it is at least once granted, it's enough for us.
Okay.
Yeah, you need to put the knife somewhere, right? In order to make this type of.
No, the knife is like you're expanding the pie quite a lot. The referee will look. It makes you will get published, but there is a difference between what I'm suggesting is very hard. It's much harder.
I know. It needs a lot of qualitative work inside, a lot of reading of what these patents are, right?
I read them, but you don't need to read them. You need to understand what they are. So why don't you take a control group of about 200 patents, where you read the abstract, and just you're glancing at the abstract, you can immediately, nanoseconds, find out if it's what you need. So with 2 days of work, you have randomly created a sample of 200 patterns, and see if your results resemble the results that you find from your gross sample.
That's great idea. It could be just a good robustness check.
Yeah, because
By the
you're going
way.
to need it. Sorry for butting in.
No, thank you. It's a really good suggestion because it's work in progress. So I need it. So yeah, and that was our sample, basically, our data set. And now I'm going to talk to you about related technological advantage. Dimitri, I don't see the time, and I think that I'm out of time.
Yeah, you're supposed to have like 4 minutes, but feel free to conclude without rush.
Yes, the related technological advantage actually counts the share of patents of each region over the sum of patents of all the technologies in one region and the sum of all regions in one the European share of all technologies of the European share of one technology in over all technologies in Europe. So we did this for photovoltaics, and that's the image we get. A region can have multiple technological revealed technological advantages, and in the first period we observed that most advantages in photovoltaic segments were concentrated in Germany, while in the last period they are spread in Western Europe, but also quite extended in Eastern Europe. Similarly, a similar count is the one of the revealed scientific advantage, and it shows the advantage that in terms of scientific publications that a region has over the equivalent share of the same PV segment in the rest of Europe. And yeah, also regions can have multiple scientific advantages. And here, if we compare the two maps, you see that actually it's more extended, the regional scientific advantage in Europe than the regional technological advantage, more diffused. So we have two models. So we used two models, entry and exit model. We used a probability panel, linear probability panel data model with time, segment, technological segment, and country fixed effects. 263 NAT regions that had at least one patent in PV. And the first dependent variable is the entry. That is entry 1 or 0 if there is no entry of the region in the new photovoltaic specialization. Regions without entry that they had already entered this specialization, this specific photovoltaic segment, were excluded. That gives us 5,556 potential entries. Now, the exit model, we used also an exit model from exit from a certain PV specialization, exit 0, 1, if it didn't exit, it remained in the specialization, and regions without exit were excluded. So we remained with 708 potential exits. No correlation test problems. And then we had also independent variables. And the first one is, of course, the revealed scientific advantage as a binary measure. RSA measures whether a region has a scientific specialization in a PV, and if this affects its entry to a new technological specialization. It is for the hypothesis 1A. Then we created a new indicator that is the scientific relatedness density for the test the hypothesis to A1B, how scientific capabilities in a PV region related to certain PV segment affect the entry of a region to a new technological specialization in this segment. So how the regions are related between them in terms of local scientific capabilities. Then to test the hypothesis 2A, we use the number of cited scientific publications by patents, and and what is their role to the region's entry or exit from this specific PV specialization. For testing hypothesis 2B, we introduced this indicator again as a scientific citation relatedness density, how other scientific knowledge in PV that a region cites in other regions that is related to a particular PV segment affects the probability of the region in new technologies in that same PV segment. That means how two PV segments are related in terms of common scientific citation. Then, following the literature, we couldn't leave outside the technological relatedness density that actually shows how regions are related, how photovoltaic segments are related to each other in terms of wider technology, like, for example, electronics. Technologies that are not per se green, but they are wider classification. And then, because actually there are a lot of complementary and competing technologies in this technological field in photovoltaics, we had the PV segment. We added the PV segment relatedness density, which shows how much the PV segments are related to each other, how much they coincide, co-occur inside patterns. So here are the results of the entry model. You see that in all cases, the regional all specifications of the model, they have time fixed effects, as we treat 3 periods. And model 4 and 6, in model 4 and 6 we included technological segment fixed effect, and in model 5 and 6 we included country fixed effect. And in all specifications of the model, the revealed scientific advantage is positively affected the entry of a region in new technology. Similarly, the scientific relatedness density, the local capabilities. Interestingly, the external scientific capabilities, the external source knowledge by the patents doesn't affect. It's not significant for the entry of a region to new specialization. And finally, it's positive and significant, the control variables. However, what is really interesting is that in specifications where there are technological fixed effects, the PV segment relatedness density is more important than the wider technological relatedness density. That means that regions prefer to diversify in green technologies when they have competencies very close to them, closely related to the technology that they aim for. Now, in past, the exit model, that again, the RSA, the regional capabilities and the regional scientific relatedness density are important for a region not to exit from a specialization in photovoltaics. It is important to note that the control variable, the technological, the relatedness densities are not affecting the exit. or not of a region from a technological specialization in photovoltaics. However, the external knowledge, externally sourced knowledge, is important in this case for a region to maintain or not to exit the specialization in photovoltaics. Now the conclusions. Finally, I reached it. The findings indicate that regions rely mostly on their local scientific capabilities and not so much on their external scientific linkages when diversifying into new specializations in PV technologies. So the probability that European regions to keep or maintain existing PV specializations is significantly higher when the region has a strong relevant scientific base around them around photovoltaic technologies and access to scientific capabilities in other regions. Now, both scientific and technological capabilities play a role in green diversification, providing opportunities for the regions to develop new green technologies. This has relevant implications to green policies and smart specialization policies in Europe. Regional capabilities, both of technological and scientific nature, could be important for green diversification. Policy should target those green segments in which regions have built capabilities that they could exploit, for the development of green technologies. Of course, there is no study without limitations, and the limitations here are the characteristics of each technological PV segment, that they differ. We didn't take into consideration the complexity or the maturity of each segment. The national and regional institutions that are fostering or not regional green diversification. Then the comparative, there is a need of comparative research with other green technologies, although photovoltaics is the most established and most codified knowledge related green technology, but it would be nice to make a comparison. And of course, we didn't take into consideration other ways that the regions should source external scientific knowledge. For example, through interregional collaboration in patents or co-authorship of papers. And that's all.
Thank you so much, Maria.
Thank you so much.
This was very, very informative. I'm pretty sure the rest of the audience agrees with